So the first speaker is our Winton Prize winner, Dr. Kerri Donaldson Hanna from the University of Oxford, who's going to talk to us about OSIRIS-Rex, a sample return mission to a primitive solar system body. Kerri.
Okay, I'd just like to thank everyone for sticking around and hearing my talk about OSIRIS-Rex. And so I just wanted to kind of start off with and remind everyone that we're actually in the midst of an era of asteroid exploration, as space agencies worldwide are proposing and sending spacecraft to asteroids all across the solar system. And here, we're just highlighting basically all the asteroids that have been visited by some sort of spacecraft, either currently or in the past. And this includes Bennu, which is the asteroid I'll be talking about today that OSIRIS-Rex is visiting. It also includes the Dawn mission, which visited Vesta and Ceres before it recently ran through all of its propellant and ended its mission. And then, of course, I'm sure a lot of people in the crowd are familiar with the Rosetta mission, that while it was on its way to the comet, it actually studied two different asteroids. Now, of course, this slide just includes current and past missions, but there's also missions in the future planned. And so NASA recently chose two Discovery-class missions that are going to other asteroid populations. And the first is the Lucy mission, which is going to be launching in approximately 2021, and it's going to be headed to Jupiter's Trojan asteroids. And then we also have NASA's Psyche mission, which is going to go to the metal-rich asteroid of the same name, and it's going to be launching in 2022. Now, of course, I'm not going to be talking about Hayabusa 2, but I would be remiss not to show some of the beautiful and breathtaking images that have been coming down from the spacecraft recently. And so the Japanese Space Agency has sent Hayabusa 2, which is a spacecraft, to their target asteroid Ryugu, and this is the asteroid. It's now in orbit and collecting these beautiful high-resolution images. And it's already sent 3 rovers to the surface to explore the asteroid surface. And here are some close-up images of the asteroid that they were taking as they were sending in some of the rovers. And so, like I said, I'm not going to be talking about Hayabusa 2, but I would definitely recommend you to check out their website, because there's getting some really fantastic images. And they too will be collecting a sample from the surface of Ryugu and are currently trying to pick out a location for which they're going to sample. Okay, so we have all this data and we're going to get more data, and I'm sure some of you are sitting here thinking, well, why are we studying asteroids? Why are these bodies so important? What makes them so scientifically interesting? There's kind of 4 main reasons. The first is that asteroids are actually the building blocks of the planetary bodies in our own solar system. So studying these planetary bodies gives us an understanding of how the terrestrial planets and the outer planets formed. We can also make maps, compositional maps of the solar system of these asteroid populations, and they can also tell us about how the planets and other planetary bodies have migrated over the evolution of our own solar system. Asteroids also, especially the carbonaceous carbonaceous asteroids and the carbon-rich bodies, they hold clues to life on Earth. So these planetary bodies include carbon and volatiles and organics, and so they can actually provide information about what was brought to Earth to start life and potentially start the oceans on Earth. And then, of course, another main reason why asteroids are interesting is that they may provide resources for future space exploration. So, obviously, we want to explore further and further out into the solar system, and to do this, we need to have resources outside of Earth to be able to use them and go further. And so asteroids might be a key for doing that. And then finally, some asteroids in the future could actually threaten to impact Earth or come close to Earth. And so by understanding their physical properties and also the evolution of their orbits, we can come up with mitigation strategies. So today I'm mostly going to be talking about OSIRIS-Rex. This is the mission that I was recently selected as a participating scientist. So you can see that this is a sample return mission that has quite an acronym. So OSIRIS-Rex stands for Origins, Spectral Interpretation, Resource Identification, Security, Regolith, Explorer. So that's quite an acronym. So the main goal of this mission is to collect a pristine sample from a primitive carbon-rich body. In particular, we want to collect at least 60 grams of that body. And using that sample, we're hoping to address fundamental questions about the origin of life on Earth, as well as the formation of the Earth's oceans. And we're going to do this by looking at the carbon and the volatiles and the amino acids that are in the sample that's returned. The other goal is to determine the physical and chemical properties of a possible hazardous near-Earth object, and then finally look for resources and materials that could enable future robotic and manned spacecraft. So how did we get to picking Bennu as our target asteroid? So there were several criteria used for selecting the asteroid that was going to be targeted by OSIRIS-Rex. The first was thinking about the proximity to Earth, because obviously the closer it is to Earth, the easier it is to get to and to sample. It requires less time and also less fuel. So that pretty much said we need to think about looking at a near-Earth object. And so to get to the asteroid the easiest, we also realized that you need to pick an asteroid that has an orbit that's most similar to Earth. So that means it's a very circular orbit, and it also has a very low inclination. And so here is an image captured from September the 22nd, 2017, which shows where Bennu, the target asteroid, is in relationship to the Earth. And you can see this blue line, which is Bennu. It does have a fairly circular orbit, and on the bottom you can see that its orbital plane is inclined 6 degrees compared to the Earth's. So out of 7,000 known near-Earth objects, using these criteria, it down-selected it to 192 possible candidate asteroids. And then, of course, as I said, we wanted to study an asteroid that might be a potential hazard. And so, just as of note, every 6 years, Bennu comes within 300,000 kilometers of Earth, which gives it a probability of impacting Earth in 2182 fairly high. So then we also want to think about the size of the asteroid. And the reason why we want to think about the size of the asteroid is that asteroids with diameters less than 200 meters, they spin so rapidly, material can actually come off of the surface and make it quite difficult for spacecraft to interact with the surface. And so the ideal choice would be an asteroid that has a diameter greater than 200 meters. And this is solely for the safety of the spacecraft and collecting the most material. And so using the criteria of size, this reduced the candidate asteroids from 192 to 26. And so here I'm just showing, this is an artist's rendition of asteroid Bennu, showing that the asteroid is about 500 meters in diameter across the poles. And if you compare that to the London Shard, it shows that it's just about 1.5 times greater than the London Shard. And then finally, the last criteria was trying to pick out an asteroid that would have this primitive carbon-rich composition and also would show signs that it hadn't been significantly altered since it was formed about 4 billion years ago. And the reason why we were focusing on these primitive asteroids is because they do contain organic molecules and water and amino acids. And we know this because we can compare telescopic spectra of asteroids with meteorites that we have here on Earth. And so here on the right are telescopic spectra of Bennu. Those are the dotted lines. And then the straight line, or the lines themselves, are different meteorites that we measured in the lab. And so you can see that from the telescopic spectra, we think that asteroid Bennu is carbonaceous chondrite-like. And so using this criteria of looking for a carbon-rich primitive asteroid reduced the candidates from 26 asteroids down to 5, and Bennu was finally chosen. So the mission officially began with the launch of the spacecraft. The spacecraft was launched on September 8th 2016 at 7:05 p.m. Eastern Daylight Time on top of this Atlas rocket, and it began its journey to Bennu. Approximately a year after launch, we needed to correct the spacecraft's orbit to actually match the inclination of Bennu's orbit. And so to do this, it flew by Earth and got a gravity assist so that the spacecraft went from the Earth plane to the Bennu orbital plane. While we were doing the flyby, they turned on several of the instruments to see if they were working, and they got a really stunning image. This is a color mapcam image of the Earth. You can see that this is the Pacific Ocean. Australia is down here at the bottom of the screen, and then Baja California is kind of up at the screen. And because the cameras were designed to image something very dark, which is the asteroid, the exposure time is very short compared to, the exposure time is quite short, and because of that, you end up getting these little artifacts at the top of the screen. Now, we also turned on the spectrometers at that time, and so at the left, I'm showing you reflectance spectra. So this is sunlight that's been reflected off of the Earth, and you can see there's a small circle here showing where the sunlight was measured. And then we also looked at the heat that was emitted by the Earth, and they did this pretty much close to the equator, and so this is the heat that we measured across the Earth. And so these were really fantastic images and data showing that everything was working just fine. Since the Earth gravity assist, we've begun what they call the approach phase of the mission. And during the approach phase of the mission, we started this approximately in August of 2018. And we will be in this phase until December 3rd when we arrive at Bennu. And during this phase of the mission, the spacecraft has been slowly braking and slowing down so that it can engage with the asteroid. And so here, what I'm showing are 3 different snapshots of Bennu as we are approaching the asteroid. And so here on the left is one of the initial images where we saw Bennu at 13 pixels. At 100 pixels, you can start resolving boulders on the surface. And then this is just a recent image with Bennu at 200 pixels. And so we can now resolve the whole asteroid, and we can see boulders and we can see color differences. And so during the approach phase, the main goals of the mission are, 1, they wanted to acquire Bennu in the cameras. Check, we did that. They wanted to also investigate whether or not there were any potentially hazardous moons around the asteroid. And then they also wanted to start understanding the shape of the asteroid as well as the spin state. And so here I'm just showing the 2 hemispheres of the asteroid that have been stretched. And this really shows that we're looking at a really complex, interesting body. And so the brightness of this image has been stretched in such a way the materials of different properties are being highlighted by their differences in brightness and darkness. And so we can see this really interesting boulder that's here on the edge, and then we can also see that you have these very dark regions scattered across the surface, but then we also see bright regions. So these are really tantalizing images to start thinking about what we're going to see when we actually arrive at Bennu and start mapping. And so this part of the mission begins on December 3rd, so we're just over 20 days away from arriving at the asteroid and start mapping the surface in detail. And so during the preliminary survey and mapping phases, we're going to be improving the topography and shape models that the teams will be using, and then they'll also be fixing the spin state, and then finally starting to map and looking at composition. And to do this, we have a suite of instruments on the spacecraft. The first is the laser altimeter, the OSIRIS-Rex laser altimeter, also known as OLA. And so OLA will be sending laser pulses to the surface of the asteroid and receiving those signals back and measuring the topography and the surface elevation, similar to what was done with Vesta by the Dawn spacecraft. And this will give us a good understanding of the surface geology. It'll improve the shape model, and it'll also help us pick out a landing site because it'll give us an idea of the slopes of the surface. There's 2 spectrometers on board the spacecraft. There's one that measures the reflected sunlight off the surface, and that's the visible and infrared spectrometer called OSIRIS. And then there's also a spectrometer that measures the heat that's coming off the surface, and that's the thermal emission spectrometer called OTES. And so these 2 spectrometers will be used to map the composition of the asteroid, in particular trying to find different minerals and primitive materials. And again, we'll be making maps similar to what's been done for Vesta using the Dawn spacecraft. And then finally, there's a state-of-the-art suite of cameras that's on the system. There's 3 different cameras. And using the cameras, we're going to be mapping the asteroid surface at all spatial scales. And so this will allow us to look for areas where we see fine-grained materials, like was found on Itokawa, as well as boulder-rich regions. And these images will help us figure out areas to sample, as well as understand the surface geology of the asteroid. And so after several months of collecting all this data, we will bring all these maps together and try to pick a sampling site. And so there are several criteria that's going to be used for picking a sampling site. The first is they're going to look for areas that are fairly flat. And these regions are of high interest because those are the easiest to engage with the spacecraft. So it's the safest location. Also, they've tested the sampling mechanism, and they've realized that the sampling mechanism works best on fairly flat surfaces. We're also going to look for regions where there's no large boulders and it's rich in loose material, because that's what we're trying to collect. We're trying to collect the loose material, and so areas that have more of it is of more interest. And then we're also going to look for regions where the spectra tell us that the material is very primitive and has been least altered by thermal metamorphism and aqueous alteration. And so once a sampling site has been selected, the sampling rehearsal begins in January 2020, and the sample collection is in July 2020. To do the sampling, they're going to be using the touch-and-go sample acquisition mechanism, also known as TAG-SAM. And so I have a movie here that shows how TAG-SAM is going to work. And so the spacecraft is going to slowly approach the asteroid. And when it gets to the asteroid, it's just going to touch the surface for approximately 5 seconds, and that's it. And during that 5 seconds, what's going to happen is nitrogen gas is going to be pushed out and burst into the uppermost regolith, and it's going to loosen the material at the very surface, and it goes into these capsules on the edge of the sample head. Also, to ensure that we get some amount of sample, they've also added Velcro, or a metal-like Velcro around the sampling head, so that when the sample head just touches the surface, the material will be collected in that metal Velcro. And so they're hoping to get some of the finest materials in that metal Velcro. And so there's enough nitrogen on board to try this 3 times. And the goal is to get at least 60 grams of material in this process. Perfect. So once a sample has been acquired, the spacecraft can depart from Bennu to make its journey home in March 2021. It'll take about 2 years to get back to Earth, and will arrive in September 2023. As the spacecraft is approaching Earth, just 4 hours before it would actually enter the Earth's atmosphere, the spacecraft will jettison the sample capsule here. And it itself will make a maneuver to put itself in an orbit, a safe solar orbit. And so the capsule will head to Earth, it'll enter the Earth's atmosphere and fall into the Earth's atmosphere until at about 3 kilometers above the Earth's surface, a parachute will be deployed, and it will safely fall down to the surface into the Utah desert. So just briefly, I thought I would talk about what we're doing in Oxford in preparation for OSIRIS-Rex. And so basically what we've been working on for the past 2 years, 3 years in fact, is looking at Bennu-like materials in the lab. And when I say Bennu-like materials, these are meteorites, minerals, and mineral mixtures that we think are most like what will be on Bennu. And we've been measuring them in our lab facilities. These measurements will be used to compare to the spectral observations that the spacecraft is making in an effort to make maps of the surface composition. And we'll use those compositional maps to select a sampling site and then also put the sampling site in context with the rest of the asteroid. And so we're using facilities within the planetary spectroscopy facility at the University of Oxford. Here is one of the environment chambers that we've been using. Here's just a diagram of how the interior of this chamber works. But essentially, we can simulate the near-surface conditions of the asteroid inside of our chamber, and we can put samples in this chamber, heat it up in the same way they would be heated on Bennu, and then measure the heat that's being emitted off of that surface using our spectrometer. And what we get are spectra of these materials. And so here I'm showing a spectra of 2 carbonaceous chondrite meteorites, ALH 83100 and Murchison. And so what we can do is we can collect all of these spectra and put them in the equivalent of a spectral library. And so once we start making measurements by the spacecraft, we can compare spectra that are in our library against what the spacecraft is seeing, and we can start identifying what materials are across the surface. Now, we're not the only ones that are working on OSIRIS-Rex. There's actually a whole host of other UK scientists that are working on OSIRIS-Rex. We have colleagues Sarah Russell and Ashley King at the Natural History Museum who will be investigating the origins and evolution of these materials using facilities at the Natural History Museum. We have Ian Franke, who's at the Open University, who will be looking at isotopic compositions of volatiles and organics to better understand where those materials originated from. And then Ben Rositas, who's also at Open University, is going to be doing a lot of detailed thermal modeling. And this thermal modeling will be really important for picking a sampling site and also understanding the physical properties of the asteroid. And so with that, we'll end, and I'll thank you for listening. And I just want to give a final plug to the mission's website, asteroidmission.org, because it's a really fantastic resource, and I stole many of the figures from that website. So with that, I'll take questions.
Okay, what a fantastic mission. There must be some questions for Kerri. Yes, please.
Just a quick question. What's Bennu's rotation rate?
It's approximately 8 hours. I think, yeah. Yeah.
Other questions? Yes, please.
Yes, a fabulous story. I mean, I've been completely out of this stuff in recent years, but I had no idea that there was a mission planned to a carbonaceous asteroid. My question is, to what extent do you expect the material on the surface of this object to differ from the C-type asteroids, which I think are mostly in the outer main belt, in view of the much greater flux of solar ultraviolet and solar plasma, the solar wind? I mean, with organics, that's likely to have done some interesting things to the chemistry, isn't it?
Yeah. So Ashley probably could answer this question better than me, but so Bennu is actually a B-type asteroid, which is a class of the C-type asteroid, which essentially means they're visible in near-infrared spectra, mean they look similar. they're slightly different, just in the way their slopes are. And so that would indicate that their compositions are similar. At least initially they should have started out different. But, as you said, as things get closer to the sun, things heat up and become altered. And so certainly that's one thing that we're really interested in tracking, and something that Ashley and students have been working on at the Natural History Museum is trying to measure things in the lab so that we can identify things that have been thermally altered based on their spectroscopic signature. And that's something that we're really intrigued to try to find.
Is the presumption that it's been in that orbit for most of the age of the solar system? Or?
That I'm not sure.
Difficult to say.
Yeah.
Thanks.
Simon Green at the back.
Thanks. Just to answer that last question, it can only have been in this orbit for a few million years. The dynamical lifetimes are only a few million years for NEAs. My question actually relates to the close-up images of at least a subset of the surface of Itokawa, which seems to show a complete dearth of small particles. If you discover on Bennu, which looks very similar, at least superficially from a distance, that this is the case, what's the efficiency of your collecting mechanism to actually be able to pick anything up?
Yeah, so I think the TAGSAM sample head is efficient at sizes of centimeters and smaller, which obviously when we were looking at disk-integrated observations of Bennu, it suggested that that was a reasonable assumption or working number. But obviously, when Hayabusa 2 got to Ryugu, they found a lot more boulders than they were expecting, and they've had to delay the sampling because of that and come up with different strategies and think about practicing and really better targeting. And so, if we get to to Bennu and there's similar issues, I'm assuming that, we have a long period in time in which we can reconnaissance the surface, and we have all those time built in for doing the rehearsals to really make sure that we get as much sample as possible.
That's fantastic. I think, Paul.
If your touch and go is going to touch and go 3 times, do you have a mechanism in place to be able to keep the sample collected at each of the 3 locations separate?
Yeah, so we're hoping to only have to do one sample and get it from all one location, because to my knowledge, no, there is no way of separating where if we had to do multiple touchdowns, which would mean that you're mixing materials. Yes.
Okay, Kerri, thank you so much for
Thank
that.
you.
That's tremendous.